All right, so just to reiterate, the directions are asking us to fill in the following table of values and also sketch the graph of the following. Now, what I notice here is I have y is equal to 2x. Now, more specifically, I notice that I have a variable in the exponent. Now, whenever you have a variable in the exponent, you have an exponential equation or a function, whichever way you want to think of it, doesn't really matter, they're the same thing. But moral of the story is that we have in this situation, in both of these situations, a variable in the exponent, that means we have an exponential equation. Now, let's go ahead and plug in some values. Now, I'm going to start with 0 because there's a little thing you have to remember whenever you have a 0 as an exponent. So let's go ahead and plug in that value and see what we end up with. Y is going to be equal to 2 raised to the 0. Now, remember that anything raised to 0 has a specific value. That specific value is 1. Now, if you remember from algebra 1, it has something to do with like multiplicity and all that good stuff. But all you really have to remember, at least for today, is that anything raised to the 0 equals 1. So 2 raised to the 0 equals 1. So if you plug in 0, you get a 1. Let's go ahead and plug in our 1 now. So y is going to be equal to 2 raised to the 1. Now, what really exponentials are telling you to do is to multiply the base that many times. So I'm going to multiply 2 by itself 1 time, which sounds kind of awkward, but it really is just itself. So 2 raised to the 1 is just 2. Let's go ahead and plug in our value of 2. So notice we have 2 raised to the 2, which is just 2 times 2, which equals a positive 4. So you notice here that those are a pretty good set of values, but I want to make sure to also plug in my negatives because this is just, again, all remembering your rules of exponents. Let's start with plugging in a -1. So notice here that I'm going to have y is equal to 2 raised to the -1. Now notice you have your base raised to a negative number. Now, if you remember, if you ever have a negative exponent, the way we deal with them is remember that you just really just flip them across the fraction. So you notice here our base is a 2, it's in the numerator. If I move it to the denominator, the action of moving it makes that exponent a positive. Now notice I don't have anything in the numerator, so I'm going to make sure to have a place value of 1 there. And now the reason why I move it down is because you can't really do operations with a negative exponent. It just really doesn't click that well. So that's why you have to deal with it. Make the exponent a positive just by moving it to the opposite side of the fraction. Moving it makes it a positive, and now you're ready to deal with whatever's left over. And 2 raised to the 1 is 2. So you notice that when you input a -1, you end up with a 1/2. Let's go ahead and do the same thing with this -2. And I'm going to do it up here just for space purpose. So y is equal to 2 raised to the -2. Again, you can't really perform operations with a negative exponent. The good thing is it's really easy to get rid of them because all you have to do is move the base to the opposite side of the fraction. The action of moving it makes that exponent a positive. Now, don't forget, if you don't have anything in the numerator, you need a place value of 1. So I have 1 over 2 squared. Remember that 2 squared is just a positive 4. So you can see that I have a positive 4 right over here. So that's cool and all. Let's go ahead and graph it to see what this is going to look like. -2 and 1, -2 and 1/4 is roughly right about there. And again, you don't have to be exact, but just get a good kind of grasp of what your graph's going to look like. -1 and 1/2. It's going to be a little bit more above. Of course, again, don't be too crazy on specifics. 0 and 1 is going to be right there, a little bit easier. 1 and 2 right here, and then 2 and 4. So I'm sure from your past experiences, if I were to connect this, because this is really just continuous, you're going to get that little like curvy shape. Now let's fill this out a little bit better. Notice that if I am looking for what is happening to my graph as I'm going down in this direction, which really what I'm looking at is I'm looking what happens when my x values get less. So if you look at your table and you look at your values as they're going up, so to speak, in respect to this table, what is happening to your y values? You'll notice you have 4, 2, 1. You're dividing by 2 each and every single time. 1 divided by 2 is 1/2. 1/2 divided by 2 is 1/4, so forth and so forth. So notice that if you divide something over and over, are you ever going to get to 0? And the answer is no. So what I want you guys to make sure that you guys do is to understand that this line, your graph, is never going to cross the x-axis or your y at 0. It's never going to cross it because you can never have your y equal to 0. Now let me go ahead and make that red so that way you can see it. This is supposed to be my y equals 0. Notice that I tried my best to make sure that that green graph doesn't go past it. And now let me go see what happens with my other way. Let's say I'm going my x's down, so I'm looking for when my x's are increasing. What is happening to your graph? Well, I notice it's multiplying by 2, so it's going to go keep on going and going and going all the way forever. So this is what is called an exponential graph. Notice that it has a little curve to it. So it's kind of just a memory game too now. So whenever you see a graph with that little curve, you're like, oh man, that looks like it could model an exponential equation. And when you have an exponential equation, you know it's going to look something like that. Of course, it can be translated left and right, but for the most part, it's going to take that general shape. All right, so we just talked about how in the world do these patterns show up within a table when you're dealing with a specific exponential equation. So you can see here that I have 2. 2 is getting raised to a variable, which is x. That 2 is what I call a base, or what everyone calls a base. Now, what's really cool about this base is that every time you increase by 1, so if you're adding 1 in the x direction each and every single time, you're doing something very specific to the y values. You're multiplying it by 2. That's why we call that base the growth factor, because notice that in this situation it's growing. And that's this growth factor, by the way. Some call it a multiplier. There's different ways of thinking it. As long as you know that every time you add 1, you are multiplying by 2, you can actually use that to be able to solve, or to be able to fill out these values really, really quick. But notice that there's also a very specific value, something else that I want you guys to see. And that is this value. Notice that whenever when you plug in a value of 0 in for your x, let's say we plug it in, anything raised to the 0 is always going to equal 1. So you know that if you have an equation just like this, like 2 raised to the x, you know that when you plug in a 0, you're going to get a 1 out automatically. Now, let me show you how this is going to help us pretty much use these patterns to be able to solve this really quickly. Now, automatically, just like I said, here's a value of x equals 0. When you plug in 0, what do you get out if you were to plug this in? A 1. Anything raised to the 0 is 1. So we already have that. Now, notice that our base, what is getting raised to that variable exponent, is a 1/2. So if it's getting raised to the 1/2, I know that each time I add 1 in the x direction, I'm going to multiply by 1/2 going down. So you can see here that I'm actually can do this really quick. 1 times 1/2 is just 1/2. 1/2 times 1/2 is 1/4. If you don't quite remember how to multiply fractions, I'm going to show you how to do 1/2 times 1/2. All you have to do is multiply across. What I mean by across is numerator times numerator, denominator times denominator. 1 times 1 is 1, and then 2 times 2 is 4. So notice that if you wanted to continuously keep adding values, it wouldn't be that hard. You can just go 3, 4, 5, and just keep multiplying by 1/2 and 1/2 each and every single time. Because again, every time you add a value, you're just multiplying by your base each time. But how in the world am I going to figure out what my value is of -1? Well, I know as I'm going down, if I'm adding a value of x, a value of 1 to each of my x's, I multiply. Well, what's the opposite of multiplying? I would say it's dividing. So if you're trying to find values backwards, you're going to not multiply by 1/2. Let me change colors so that way there's no connection between these two. Once you're multiplying, you're going to divide by 1/2 now. Now, whenever you divide by a fraction, it's the same thing as multiplying by the reciprocal. So let's flip this. And notice you end up with 2/1. We can see here that 2/1 is the same thing as multiplying by 2. So if I'm starting at 0, which I know it would be my value of 1, and I go back 1, well, I'm just going to do the opposite of multiplying by 2. So 1 times 2 is 2. You'll notice that it's a little bit easier with whole numbers, and then 2 times 2 is 4. So that was a huge explanation on how to use pretty much your base to fill in a table really quickly when dealing with exponential functions. Well, you'll notice here that we could actually use this for future. So again, work on it, see if you got it. Let's go ahead and graph this. -2 and 4 is right over here. -1 and 2 right over here. 0 and 1 is right over here. 1 and 1/2 is right about there, and then 1/4. And just like before, notice that I have this little shape of graph. I'm trying to figure out what happens to the end. we're trying to figure out what happens over here. Well, that's where my x's get less than. So if you look at your and analyze your graph going up, notice it's getting bigger and bigger and bigger and bigger. So it's just going to keep increasing in the positive direction. Notice if you work backwards, you're going to 1/2, 1/4. You're just dividing by 2. So you're going to get very close to 0, but you're not ever going to get there. So you'll notice here that I have very 2 specific situations that we are going to focus on later. But while we fill out a couple more of these or do a couple of these tables to really practice the patterns within the tables, try to analyze and be like, I wonder why one goes up and one goes down. You'll notice that for the most part, it's going to be your factor, your multiplier, your growth factor, or technically decay factor in that instance. All right, cool. So any questions before I erase all this stuff? All right, so let's go ahead and I'm gonna have you guys do these following too. Now, keep in mind that I do want you guys to use the patterns that we just covered above. Notice what happens when my x is 0 with exponential functions. What would be my y value? So the main thing I'm focusing on here are shortcuts, shortcuts, and shortcuts. I don't want you just to plug these in and do all the math because obviously we're growing on something that we already know. All right, guys, so let's fill in this table. Pretty much focusing on the patterns that I know are true given this exponential function. So the first things first is I know that whenever my x value is 0, and I just have a base raised to an exponent, well, I know that that base raised to 0 is always going to equal 1. So I know that that value alone is going to be 1. Now, I notice that whatever is getting raised to the x is my base. So that is what I like to call, or what people call your multiplier. Now, this is pretty much a pattern that whenever you add 1 to the x values, what you're really doing is just multiplying by whatever your multiplier is. So that's why sometimes a lot of people like to remember exponential patterns, I guess, within tables as an add multiply pattern. Because as you add 1 to the x direction, you're multiplying by whatever your multiplier is. So it's kind of just a way to remember the general patterns that are going on here. So I can see here that again, you can really see that your x's are adding 1. So you can focus on your y's and be like, okay, 1 times 4 is 4, 4 times 4 is 16. So you have those values. And again, you didn't have to plug them in. If you were to plug them in, you'll notice you get the same thing anyway. Now let's go ahead and work backwards. Now, what's the opposite of multiplying by 4? Well, it is dividing by 4. And 1 divided by 4 is just 1/4. And 1/4 divided by 4 is 1/16. So you can see there that it was quite quick the way I graphed these ones. -2 and 1/16 is going to be really close to 0, which is right there. -1 and 1/4 is a little bit above 0 and 1. 1 and 4 right over there. And then 2 and 16 is going to be way off the charts over here, which makes sense because if you notice, if I were to connect these coordinate points, you'll notice you have that little exponential there. Now let's go ahead and look at number 2. Really quickly, again, you're going to get better the more you see these. Notice that you have a base getting raised to an exponent. Whenever you raise to that base to a 0, you're going to get a 1 out. Let's go ahead and multiply by 5/4. 1 times 5/4, because again, I'm adding 1 to the x direction. 1 times 5/4 is 5/4. 5/4 times 5/4 is 25/16. And you could go ahead and work backwards to do that too. So remember, let me write this out to make sure that we have a good understanding. So the same thing as since I was multiplying by 5/4, the opposite would be to divide by 5/4. And if you're ever dividing by 5/4, the same thing as multiplying by the reciprocal. So notice that this is a multiplication sign. All I did was flip my inequality because I know that division and multiplication are the same thing, but just a little different. So notice right here, I'm going to take that 1 and multiply by 4/5, which is 1 times 4/5 is 4/5. And then multiply it again by 4/5, which gives me 16/25. So now that I have that, I can go ahead and graph this. Let me start with my 0 and 1, which is right over here. 1 and 4/5, -1 and 4/5 is roughly there. -2 and 16/25 is roughly about there. 1 and 5 is going to be roughly there. You can see that I have enough coordinate points to pretty much do it. I'm not going to be too specific on the graphs, just as long as you have a pretty good look there. So you can see here that the domain, the x values that can be plugged into this graph are all the real numbers that we could think of. They include everything. And then notice that your range are very specific because it's never going to get to 0. So you know that your y values are always going to be greater than 0. And this goes for any of them. Notice that if you have an exponential, at least a non-translated one, your domain values, again, are going to be all your real numbers, and then your range is going to be when y is greater than 0. So anybody have any questions on these two problems? All right, guys, so let's put this into a super mathematical kind of note-taking way. So let's say we have a general equation that's y is equal to some base raised to an x, and that can also be written in function notation. Now, whenever you have this situation where your b is greater than 0 and your b is not equal to 1, well, then you have an exponential function. Now, the good thing is that if you're ever filling out a table, my recommend or graphing in general, start with values that you know are really easy. Always know that if you plug in a 0, you're always going to get a 1 out, no matter what that b is. It's always going to be true. Now, keep in mind that every time you add 1 in the x direction, you're going to multiply by whatever your b is, whatever that base is each and every single time. And of course, working backwards, you're going to do the opposite. Now, keep in mind that if that b is greater than 0, so if it's 1, 2, 3, 1.5, you're going to have something that's called an exponential growth, because since you're multiplying by something bigger than 1, it's going to keep growing. So that's why we call it exponential growth, and that is what your graph will look like. Now, let's say we have a different situation. Let's say that that b is greater than 0, but less than 1, aka it's a fraction between 0 and 1. Well, then you're going to have something that's called the decay. Now, why is it called the decay? Because notice that no matter what, if you still plug in that 0 for x, you're still going to get a 1 out. But every time you add 1 now, you're going to be multiplying by the b, but this time that b is a fraction between 0 and 1. If you multiply a fraction between 0 and 1 to anything, it's going to get smaller and smaller and smaller. So what that's going to say, it's going to flip your graph the other way. You're going to start big and go super small. So that's what we call a decay, because notice that is decaying down. One thing I want you to pull from all this is to make sure that you understand that these graphs are continuous. So make sure you connect all your points, and you have arrows to kind of show that it's going forever. Your domain are always going to be all real numbers. There's no value that you cannot plug in. Your range is always going to be y is greater than 0, at least for these ones, because your graph is never going to touch 0. And asymptotes, don't worry about it, because we really haven't covered those for now. But we'll cover them probably a little bit later, probably in regular. So that's pretty much it for that. What I want you to do now is to use that information and tell me which one of these, A through F, is an exponential growth and exponential decay. We'll go over these in not even in 30 seconds. All right, looking at A here, I'm asked to decide whether this function is an exponential function. So the first thing I want to look for to see if I have an exponential function is if I have a variable in the exponent. Now, I notice here that I have a variable in the exponent, so that means that yes, this is an exponential function. Now, since that's an exponential function, I can decide whether it's a growth or decay, aka whether it's going to be a growth like this or a curve down and be decaying. Super easy to find, because all you need to do is look at your base. Notice that this base is a 1/5. It's a fraction between 0 and 1, aka every time you multiply, it's going to be getting smaller and smaller. That means that this is a decay. If you were to figure out your values, you'll notice that it's facing down. All right, very next one. Do you have an exponent in the variable? Yes. So that means that this is an exponential function. Is your base a fraction between 0 and 1, or is it greater than 1? It's greater than 1. If you keep multiplying by 1/2, it's going to get bigger. So that means that this is a growth. Very next one, notice that you have another variable in the exponent. So it means that, yes, this is an exponential function, and it's going to be specifically a growth, because what is getting raised to the x is a number greater than 1. Multiply by 3, you're going to keep getting bigger. Now notice that in this specific problem right over here, do we have a variable in the exponent? And the answer is no, because we have a constant in the exponent. So that means that this is not a function. Looking at E, you have a variable in the exponent, yes, but it's negative. Keep in mind that your exponent cannot be negative, because it's going to lower it down. So you're going to end up with 7 raised to the 2x. So this is not a typical exponential function. It's something a little more complicated, so don't worry about it. So no, this is not an exponential. Notice the very next one, you have a pi. height is a variable, but it's a variable representing a specific constant. So this is not just a variable that changes. So this is no, it is not an exponent. It's not an exponential function there. So that was my goal here, is to kind of show you guys these set of problems so that way you guys know what an exponential function is. And you'll be able to graph it if you ever see one. Now, before we go on, notice that I want to give you a little bit more difficult problems. So I want you guys to start with just the first one here. Start with the first one, see what you got. Notice that this value changes things just a tad. So try to go over these, see what happens if I have a multiplier out in front. And then we'll go over these in roughly about 5 minutes or so. Okay, guys, sorry about the wait. I want to make sure that if you have any questions, let me know before I go over this one. All right, cool. So, you'll notice in this situation, we've added a little bit of something. We still have our base as getting raised to the x. Now, the nice thing about this is that your base in terms of your growth factor and what is multiplying is still going to be the same. As you add 1 to the x direction, you're still going to multiply by whatever that base is. But notice that 3 is going to have a little bit of change. And that change 100% has to do with where you're starting, aka when you plug a 0 in, what happens to this situation or this table? Y is going to be equal to 3 times 2 raised to the x. 2 raised to the x of value of 0 that we're plugging in is going to equal 1. So you end up with 3 times 1, which equals a positive 3. Now notice that that 3 pretty much is a shortcut because you don't even have to think of 0 and 1, because all you have to do is think of whatever that number is out in front is going to be that value, because it's going to be 3 times whatever 1 is, and anything times 1 is itself. So it's kind of even easier to just focus on that little number out in front and just start with 0 and whatever that number is, and then use your multiplier. 3 times 2 is 6. 6 times 2 is a positive 12. If you were to work backwards, the opposite of multiplying is dividing. So 3 divided by 2 is 3 halves. 3 divided by 2, 3 over 2 divided by 2 is 3/4. And you have your table. So if I were to graph this, 0 and 3 is right over here. 1 and 6 is roughly about there, and then 2 and 12 is somewhere way out there. Negative 1 and 3 halves seems about right there, and you'll notice that that's pretty much enough to draw my graph there. All right, so a little bit quicker for this one. Notice that this time I just don't have a base raised to an exponent. I also have a multiplier out in front. That 6 is multiplying that 1/2. Luckily for me, I already know the effect that it has on a graph, because all you have to do is plug in your 0, and it's going to always equal whatever that value is. That's multiplying. Now notice that your multiplier is 1/2, so I'm just going to go ahead and every time I add 1 to the x direction, I'm going to multiply by 1/2. 6 times 1/2 is just going to be 3. 3 times 1/2 is 3 over 2. If I were to work backwards, starting at this point, well, what's the opposite of multiplying by 1/2? Well, it's dividing by 1/2. And if you're dividing by 1/2, it's the same thing as multiplying times a reciprocal, which in this situation is just 2 divided by 1, which is just a 2. So I can see here that this one's a little bit easier, right? All you have to do is multiply by 2 all the way up. If you were to graph this, negative 2 and 24, somewhere way out there. Negative 1 and 12 is not that far. And then 1 and 3 is roughly about there. 1 and 3. You'll notice that you have some looking graph like that. Now, where is the majority of your points going to come? The majority of your points are going to come from this section here, the table, making sure you understand those values and know how to do them. So let's see. And the main reason why I want to go over this is because notice if you ever have an exponential function with a multiplier out in front, that a there, that tells you a lot of information, but you've already built on a base pretty good enough. You know that whenever you plug in a 0, it's always going to equal whatever that a is multiplying that base towards the exponent, and nothing else changes. When you go up by 1 or increase by 1 in the x value, you're still going to be multiplying by whatever that b is. Now, it doesn't matter if your b is greater than or equal to 0, you're still going to have a growth, and when you have a decay, you're still going to have the same thing as well. So majority of the story there is that we just took a little bit of extra time to make sure that you know, hey, if we added this little piece, don't get too hung up on it. It's almost really the exact same thing. So